Hi, we're Group 6, and our members are Devin, Isaac, Natsu, Sihan, Samuel, and Holly. Our project is about a hybrid encryption messenger. Almost everyone who has a phone has some kind of messaging app and uses it daily. Some of the most popular ones include WhatsApp and Facebook Messenger. Despite messaging apps being such a useful tool, not all of them are built in a way that is secure for everyone to use. The standard for encryption in communication apps is end-to-end encryption, which is a safe way to ensure that messages are only seen by the sender and recipient. Not all messaging apps offer this. Even for some apps that claim they do, it's only part of it. Some apps have limited scope and only offer end-to-end encryption in certain circumstances or if the user manually enables it. With many companies not providing enough when it comes to security, users of these messaging apps could face internal and external threats that compromise their safety. Knowing all of this, we wanted to create a messaging app that would ensure the communication between the sender and receiver was secure. Through our research and knowledge we learned from class, we found different encryption methods we could use on our app that would make it as secure as we possibly could. Our goal was to create a unique and functional app that could give users the authenticity, confidentiality, and defense they need from their communication apps.
We chose to use a hybrid encryption approach since each algorithm provides different strengths. Individually, they cannot provide complete security for our messaging system. Diffie-Hellman gives us a secure way to generate a shared secret key between users, even over an open network. However, Diffie-Hellman on its own cannot verify the identity of the user you're messaging. Because of that, an attacker may attempt to intercept the exchange and insert false key values. To solve this, we integrated RSA digital signatures, which authenticate Diffie-Hellman values and confirm that they truly came from the intended sender. RSA is not efficient for encrypting large amounts of data during an active conversation, which makes AES 256 important. AES is optimized for real-time communication, which makes it ideal for encrypting every message following the handshake. AES requires a strong secret key, so Diffie-Hellman provides a new one for every session. By combining all three algorithms, we created a layered system, with each component covering the other's limitations. Altogether, this gives us secure key exchange, reliable authentication, and fast encrypted messaging. By combining Diffie-Hellman, RSA, and AES 256, our app provides various key security guarantees that align with standards for private communication. First is confidentiality. AES 256 encrypts all messages, meaning only the sender and receiver can read them. The 256-bit key size creates a large key space, which makes brute force attacks mathematically impossible. Diffie-Hellman ensures the AES key is secret and unique to the current session. Next is integrity. RSA digital signatures verify that the exchanged key material hasn't been modified. This prevents attackers from tampering with the handshake or inserting forged values. Furthermore, authentication is achieved with RSA and Diffie-Hellman. RSA confirms the identity of the communicating parties by validating the Diffie-Hellman values. This blocks man-in-the-middle attacks and ensures the session is established between legitimate users. Another benefit is forward secrecy. Because we use Diffie-Hellman, a new key is generated in every session. Even if one RSA key were compromised in the future, past encrypted messages will remain secure. Finally, our system provides defense, meaning multiple cryptographic layers work together to protect the conversation. Even if one component were targeted or partially compromised, the other layers still maintain overall security. This layered structure significantly strengthens the reliability of the app's encryption.
For our app, we use Diffie-Hellman Ephemeral, or DHE, as our key exchange protocol. This allows two users to securely agree on a shared secret key without ever sending the key across the network. Both users publicly agree on two values, G and P. These are not secret, and then each user picks their own private number and computes a public value based on it. The public values get exchanged openly, and then each slide performs one calculation with its own private number. Even though both sides send some information over an insecure channel, only two users can compute the final shared secret key. So a new Diffie-Hellman key pair is generated for every session, which provides forward secrecy. That means that if one session key is compromised, previous conversations can still stay protected. However, this does have one big weakness. There's no authentication built into DHE. That means that an attacker can perform a man-in-the-middle attack by intercepting both public keys and replacing them with their own. Without authentication, each user can think that they're talking securely, but an attacker can just sit in the middle, decrypting and re-encrypting both sides. This is why for our actual message encryption, we use AES. Since AES is a symmetric, both users need to share the same AES key. Uh, since we can't just send the key over the network in plain text, we use DHE to securely generate it. Then we fix DHE's authentication problem by using RSA for digital signatures. RSA essentially assigns its own signature to every message, so you know that yes, this key came from the real user and not just an attacker. This combination gives us AES for strong message encryption, DHE for secure key exchange with forward secrecy, and RSA signatures for authentication against man-in-the-middle attacks.
RSA is an asymmetric encryption algorithm, meaning it has like two different types of keys, a public key and a private key. And for digital signature, we utilize a private key that signs and a public key that verifies. And what digital signature does for us is it ensures that our message actually came from the person we believe it was sent by and that it wasn't modified while we were sending it. So signing process digital signature is simple. Your message gets hashed. It's encrypted with the sender's private key. That's our signature. The signature is attached to our message, and then the receiver recomputes that and decrypts it using the sender's public key. That gives them the original hash. They verify it against their hash, and if the two hashes match, you're all good. The message was not modified. In the case of AES, which is Advanced Encryption Standard, AES is kind of the main encryption method in our app. It's a symmetric block cipher against the RSA's asymmetric algorithm, which means basically it uses the same key to encrypt and decrypt the data, making it faster, a little bit more secure, and more up to date. RSA is a little dated at this point. Basically, it works in these fixed size blocks. It takes 128-bit chunks of like plain text and runs them through operations to produce ciphertext. And that encryption is done through subbytes, shift rows, mixed columns, add round key. So are like our 4 core operations to encrypt. We are specifically using AES 256, which means our key is 256 bits long, and the algorithm runs 14 rounds of these transformations. Basically, the larger key size makes it that all of that data gets so, modified so heavily encrypted that brute force attacks are almost entirely unable to get to this data. So AES against RSA just gives us speed, stronger security, and a very low computational cost, which is why it's kind of used everywhere nowadays. Well, we don't really see RSA as much.
Now it's time to talk about the app itself. We chose Python as a programming language. While it isn't the most secure language, it suits our needs well. Our Hybrid-Encryption Messenger relies on several public Python libraries, most of which handle encryption, cryptography for AES, secrets and hashlib for DHE, and RSA for RSA operations. We also use Socket and tkinter for networking and GUI, which we'll cover briefly. Our GUI is simple and built with tkinter. It lets you select your user profile, choose who to connect to, view an encryption status indicator, and of course, use the chat log and message box to communicate. Next, let's briefly discuss the app's socket connections. Using Python socket library, devices connect by entering an IP address and port number. Because sockets require a host, and coordinating that manually can be inconvenient, our system automatically assigns the first user to connect as the host. With this setup, we can transfer data over the internet. Now we just need to do so safely. Finally, let's go over the encryption process, which consists of 6 main steps. First is the TCP connection, where one device initiates contact with another. Next, both host and client exchange their public RSA keys. These don't need to be encrypted and are used to decrypt the following step, the DHE protocol. Each device sends its portion of their secret key, signed with a digital signature to ensure authenticity. The signature can be verified using the RSA public key mentioned earlier. Once each side receives the other half's DHE, both combine them to form the shared secret. This secret is then hashed with a SHA-256 hash to create an AES-256 key. With the symmetric key established, the encryption process is complete, and all messages are now sent using AES encryption. Hello, I'm here to give you guys a little demonstration on our Hybrid-Encryption Messenger app. As you can see, I already have 2 instances of the app open. The app is pretty simple, but that's because most of the effort has gone into creating a strong encryption behind the scenes. Currently, you select your user and who you want to connect to with these drop downs here. Once you do that, it'll automatically assign the correct IP and port you want to connect to. Currently, it's just using the 127.0.0.1 loopback address, but the app is able to communicate between 2 different IPs. Whenever you're ready to start the chat, just hit the connect button on both clients. The first one to hit connect will automatically be assigned as the host, as you can see here. And I want to bring your attention to the security status monitor up here at the top. Once I hit connect on the other client, you can watch as it goes through all of the encryption steps we have set up. And we're connected. From here, it's very simple. Just type in the message box below, hit enter or press the send button, and it'll pop up on both apps, along with the name of the user that sent it. As I mentioned earlier, the app is more complex on the back end than the front, and we'll demonstrate that on the next slide by showcasing some Wireshark packet captures. To showcase that our encryption functions, here are a few Wireshark captures of our loopback address, 127.0.0.1. The top screenshots are all the packets sent when the 2 clients first connected. Port 9999 is the host, and port 57769 is the client. All of the packets are completely encrypted except for 2, the ones carrying the RSA public keys. As the RSA public key was the one thing we didn't encrypt, we can see that our program is working perfectly. We also took captures of a regular message sent using the app. Just like the other packets before it, this packet has been thoroughly encrypted, leaving no plaintext behind. These captures show that our encryptions do work, helping protect your personal information.
So, in conclusion, our project demonstrated how a secure messaging system can be established by putting different cryptography techniques into one hybrid encryption framework. Throughout this project, we have found the weakness in the current messaging applications and solved them by integrating DHE, RSA digital signatures, and AES-256 encryption. Together, all 3 components can offer confidentiality, authentication, and strong protection against the MITM, which is also known as the man-in-the-middle attacks. We decided to use DHE for secure key exchange, RSA to verify identity and sign the key material, and AES-256 for fast and strong message encryption, because we can guarantee that any communication in our app will remain private and well protected. The implementation, which was coded with Python libraries, socket, and a custom GUI, will show how those concepts can be translated into a secure messaging app with functions and features that will enhance the user's experiences. For future steps and development of the app, while our app already provides strong encryption, which is the foundation of building a safe and secure communication, however, the message cannot be saved. Once the app is closed, any chat history will be gone permanently, as there is currently no chat logs. In addition to that, the application is also missing the built-in user authentication, which means the user will not be able to verify their identities within the interface. Last but not least, the system currently doesn't allow users to add new users to their list of contacts.